Okay, we start the last chapter in our class. Okay, this is chapter 10. Okay, chapter 10 consists of 5 different subsections, okay, or sections, and it's counting methods. And mathematically speaking, so this is chapter 10, counting methods. But actually, another name of that topic is called combinatorics. Okay, this is chapter 10, and it has 5 different sections. Okay, we'll do this. We'll consider the problems in these chapters successfully. So, what is this chapter about? I need to say that this is the most difficult part of our course, because in this part we have to calculate the number of ways to do some work. So how many ways you can do this work and that work, and we'll solve different problems, sometimes very difficult ones. How many license plates in the United States, or how many telephone numbers are in the United States, in particular in Charleston and maybe in Chicago. So that kind of questions we'll solve. Okay, so in chapter 1 is called systematic listing. Systematic listing is number 1. Counting by systematic listing. Okay, what is that? So sometimes I will just read what's written in the text, and then we'll give some examples. Okay, use a systematic approach to perform a one-part counting task. Use a product table to perform a two-part counting task. Next is use a tree diagram to perform a multiple-part counting task. And the last one, use systematic listing in a counting task that involves a geometric figure. Okay, so let's start from the beginning. One-part task. Suppose you just toss a coin, and coin. Okay, coin has two different faces. Head, and another one is tail. So, and the possibilities when you toss it, you have either head, which we denote, say, by 0, and the tail, which we denote by 1. So, if you toss the coin, you will have sequence. Okay, head, tail, head, tail, head, tail, tail, tail. And this can be transformed mathematically in the sequence of zeros and ones. So we just write 0, 0, 1, 0, 1, 0, 1, 1, 1. Okay, this is mathematical representation of your process. Another possibility is to toss a fair die. Okay, so you have a die, a cube. Okay, and some numbers are written here, so I will write Arabic numbers like, say, 1, 6, no, let me just say, okay, 1, say 2, and this is, say, 4. By the way, the fair die has, on the opposite side, the total sum is 7. So this number is 3. On the bottom, on the left side is 7 minus 2 is 5, and on the back part is 6. Okay, so 6 in there. Okay, so you toss it, and the results are the numbers 1, 2, 3, 4, 5, 6. They are outcomes. Okay, so and if you toss, for example, you have the following sequence. Say 1, 2, 6, 6, 5, 4, 1, 4, 4, 3. So this is some number of tossing, and you have this sequence. Okay, so now we go to the problem. An example: selecting a club president. Okay, consider a club N with 4 members. Okay, so club N consists of the following: Mike, okay, Mike, Adam, Ted, and Helen. Okay, just if we take the first letters, you can write this as a sequence or a set. Okay, M, A, T, H. And we think you recognize this word, M, A, T, H. Okay, now we want to get, okay, choose a president of the club. President. How many ways? How many ways to choose? Okay, let me just write are there. Okay, you want to choose a president. There is only one president. Out of how many? 1, 2, 3, 4. So you can choose either M, Mike, or Adam, or Ted, or Helen. And of course, a woman should be chosen, so H is the only possibility. No, I'm joking. So how many ways? Surely it's either one could be chosen, right? So therefore, answer is, okay, 4 possibilities. Okay, namely, okay, so either, let me just write only the first letter, either N, okay, or second one, or A, or T, or H. Then you see there are 4 of them. Okay, that one is simple. Okay, 4 possibilities. That and 4 outcomes. Okay, now next problem is, let's solve a little bit more complicated problem. And that problem is building numbers from a set of digits. And I need to say that the majority of questions which we'll discuss here, and also which will be on your test, quiz, will concern kind of building numbers from a set of digits. Okay, so consider the following problem. You have digits, okay, from the set, say 2, 4, and 6. Okay. Now you create a 2-digit number. 2-digit number. And we call it like AB, and we write bar, meaning that it's not a product, it's just first digit A, and second digit is B. Okay, so question the same. Okay, question. Let me write here also question. Okay, question is the same. How many, okay, 2-digit numbers A, B are there? Okay, so that problem, it can be solved very easily. And namely, next page tells us how to solve such a problem. Okay, let's write the following table. Okay, we cross here, and let's write this is A, this is B. First digit, okay, first digit. Okay, first digit is A, second digit is B. Okay, so let's look. Digit A, it can be either 2, 4, or 6. Okay, let me give you some examples. So suppose what number could you write? You could write 26. Okay, so it's 24, 64, and so on. So how many? First digit could be 2, 4, or 6. 2, 4, or 6. And how do we write such a number AB? You just take two positions and pick one of those, say 4. After that you pick B, which could be also 2, 4, or 6. Okay. What can you write after? Okay. What can you write after digit 4? Say 2, 42. And let's look. First digit is 4, second digit is 2. And this number will be 42. Clear, right? Okay, let's write all possible two-digit numbers. First digit, let's write. Suppose first digit is 2. Then what are the possibilities for the second digit? Could be 22. Let me just circle. Okay, 22, then 24, 26. This is how we can write these numbers if we start with digit 2 and adding each digit up here. Next we take 4 and we have the two-digit numbers 42. Again, so 4 is here. Okay, 42, the first digit 4. Next digit is 2. Then 44 and 46. And finally you have 62, 64 and 66. So how many total outcomes you can, how many total two-digit numbers you can write? Surely all of those are here, and we see that the number of ways to write two-digit number using 246 is 3 by 3. 3 times 3 equals 9. You see there are 9 numbers. Important here is not the number 9 itself. Important that how we find it. Okay, we find it as follows. We take digit A, we take digit B, and we ask ourselves how many ways, in how many ways you can use first digit, letter A, okay, digit A. There are 3 possibilities, 1, 2, 3, right? 1, 2, 3. So you have 3 possibilities. To pick the other one, you have also 3 possibilities, 3. And after that, you multiply and you get 9. And why you get 9? Because how to get 9? It's just the area of this rectangle with side 3 and 3. Total will be 9. That's why we multiply. A little bit later, in the next chapter, we formulate general rule, the so-called rule of multiplication. And that rule will be the key for solving all problems in combinatoric, almost all. Sometimes they're very difficult, but the general, the basic problems based on the product rule. Let me explain to you once again how to solve this problem in a little bit different way. Just because that example is very simple, I will show you the so-called tree which solves this problem in the same way. Okay, so let's start solving this problem a little bit different. Okay, so we start with a point and call this point root. After that, we ask ourselves. What is the first digit? What is the first digit A? Okay. So let's write. So we have three possibilities. And write the first possibility, either 2, okay, either 4, okay, or 4, or 6. So we have three possibilities. And that's what we marked here, three possibilities for letter A. Now letter B. If we have 2, then after that we can extend it in three different ways. Again, 2, either 2 or 4 or 6. With 4, we can do the same thing. So we have three different extensions. Okay, 2, 4, 6. And finally with 6, you can also extend it with three different ways. 2, 4, and 6. So question is, how many 2-digit numbers can you get? Okay, now that 3, okay, that 3 answers the question, our question. For example, if the first digit is 2, next digit could be 22, 24, 26, and all of them are shown in the first row of the table. And by the way, so let's look, what is 22? If we start with root and go along the first path of the tree, you will have 22. So this one gives you 22. Okay, if you go through 2 and then 4, you'll get 24. Okay, let me just draw the arrow. 26, you get 26. Okay, you get three possibilities starting with digit 2. So if you fix 2, we have three possibilities. Now, if we start with 4, we have the following numbers: 42, okay, 44, and 46. Again, three possibilities. And finally, with starting with 6, we have the following numbers: 62, okay, that one is 64, and 66. Again, we have three possibilities. Now, after that, what we have to do? We have to count all the numbers. So we have to add 3 numbers from here, 3 numbers from here, and 3 numbers from here. What is that? It's just nothing taken 3 times. Let's write 3 times of 3. Okay, so that's why we multiply 3 by 3. And the answer is 9. Okay, that is the important part. 3 multiplied by 3. Now, the number of such 2-digit numbers, okay, why is it a tree? It looks like a tree, yes? And the ending digits here looks like leaves. Okay, you have a leaf 2, leaf 4, and so on. And after that, the number of numbers in the table is the same as the number of paths, from the root to the leaf. And surely it's clear that that each path, for example 46, corresponds to the leaf 6. And so then for the answer is 9 is the number of leaves gives you the number of all possibilities. Okay, I show this example so thoroughly because it's the simplest example that could be considered, and if you understand that, you will be able to solve more difficult problems, and also will understand the product rule. Okay, let's go to the next page, and now consider the possibilities of rolling a pair of distinguishable dice. Okay, so let's write here. Okay, rolling 2 dice. Okay, important thing, so it's in the paper it's written green dye and red dye. Important that the dyes are distinguishable. Let me just try red and green. So we just make the same table and write what will happen. So here is, say, green, I write G, and red dye will be here. So red in here, green in here. I need to take some. Okay, so if you dye one, if you toss one die, you get the outcomes 1, 2, 3, 4, 5, and 6. Okay, if you toss the second die, you'll have the outcome 1, 2, 3, 4, 5, and 6. Okay, and what could happen when you toss two dice? You can do this simultaneously, or you can do this one after another. It doesn't matter. Important, we have to know which one is first and which one is second. So first, toss the die R, red. Okay, first. Second, toss the die green. So again, as in the previous case, you have two possibilities. So that will be for red, and this will be for green. Important thing here, that red is the first and green is the second, which means that we distinguish the pair 2, 6, for example, and 6, 2. Okay, when you distinguish pair 2, 6 and 6, 2, it means that you consider the set 2, 6, but also important the order. Okay, and in this case, such a pair is written in parentheses, and usually in mathematics it's called vector. So let's write all the outcomes. Okay, 1, 1. Okay, so it's written here in parentheses. Okay, so first is 1 and second is 1. Suppose the first outcome is 1. What will be the second? Okay, let's write 1, 1, 1, 1, 1, and the second one will be 2. 2, then 3, then 4, then 5, then 6. Let me just explain once again for 2 and then write down the whole table. If you toss the first die and red one, and you'll see 2, so you can write 2, 2, 2, 2 everywhere, and then the second outcome could be any, so one of the 6. So you have 6 possibilities: 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, and 2, 6. And let me finish the other one. You have 3, 3, 3, 3, 3, 3. Here we have 4, 4, 4, 4, 4, 4. Then 5, 5, 5, 5, 5, 5. 6, 6, 6, 6, 6, 6. And then you write the same thing. 1, okay, 2, 3, 4, 5, 6. Okay, let me just, not finishing this table, I will just write something. Say, so that arrow, that square corresponds, the first die is 5, and the second one is 6. So you take the intersection, and the answer is 5, 3. Over here is 6, 2. That one is 6, 6. So that one is, say, 4, 4, 4. Okay, and so on. How many outcomes? The first outcome is A, and the second is B. Does it remind you something? isn't it the same problem as here, but in a little bit different way? So here we consider the digits 2, 4, 6 and 2-digit number consisting of these 2 digits. Now we have also 2-digit numbers, but the alphabet, okay, I didn't say this word alphabet yet, but let me just mention right now, first time. The alphabet is 1, 2, 3, 4, 5, 6. This is a set of characters from which you can choose your number or your character. And so how many of those you will have? You have 6 possibilities for A. You have 6 possibilities for B. And total here, it will be the area of this rectangle, the number of squares in that rectangle, and how many of those is 6 here, 6 here, 6 here, so 6 taken 6 times. Okay, 6 plus 6 plus 6 plus 6 plus 6 and plus 6 taken 6 times. And what does it mean? It means that 6 multiplied by 6. And total answer is 36 different outcomes. Okay, remember that, say for example 2, 4 and 4, 2 here, okay, they are distinct. Let me just color them. Okay, let me color. Okay. Okay, 2, 4 and 4, 2, they are not the same. So 2, 4 is not the same as 4, 2. But if you take, for example, 4, 4 and exchange those, it will be the same pair. Okay, so it's written on the diagonal. Okay, so on that diagonal, you have equal numbers. And if you exchange them, okay, this is 5, 5, 6, 6. Okay, on the diagonal, you have equal numbers, and you have such only 6 outcomes of those. Okay, let me just repeat once again the logic we used in the previous one. A can be taken in 6 ways. B can be taken after that in 6 ways. So we multiply those, the number of squares, the number of pairs. Each pair corresponds to 1 square. So the number of squares or pairs here, it will be 36, so this will be the answer. Okay. Let me explain to you the same answer using tree. Yeah, it will be much more complicated and I will not draw the whole one. So you start with a point, which I call root, and then for the first dice, you have 6 possibilities. 1, 2, 3, 4, 5, 6. Okay, 1, 2, 3, 4, 5, 6. Now, if you start with 1, what will be the second one? Here we have to draw 6 segments. 6 segments, and also write 1, 2, 3, 4, 5, 6. So here are the numbers 11, okay, numbers pairs 1, 1, 1, 2, 1, 3, and so on, 1, 6. Now you do the same with 2. You have to draw 6 different segments, 5, 6, and also write 1, 2, 3, 4, 5, 6. Okay, and so on. So everywhere you draw, okay, 6 lines, and write in the end 1, 2, 3, 4, 5, 6. And after that, you find the number of roots, the number of paths from the root to the leaf. Okay, one way, one path, second path, and so on. And how many paths are here? Exactly 36 paths. Okay, so that tree shows is equivalent to that rectangle, and it shows that you have to take the product. But a simpler work without table and without the tree is the following. So you ask yourself, take first digit. How many ways? In how many ways can you do this? In 6 ways. Take after that second digit. How many ways you can take? 6 ways. And important thing that the second digit is taken after the first one independently. And after that you have to multiply, about which I will tell you the rule, general rule, a little bit later. So after that you multiply. Why multiply? Because the table shows that. That's 6 times 6. The tree shows for each possibility for the first digit 1, you have 6 possibilities. So you have 6, 6, 6, 6, 6, taken 6 times, as written here, and you get the product. That's why the product comes up, 36. And that one is the general idea, which will be applied in many different cases. And I will show you much more difficult problems that based on that idea and can be solved in a very easy way if you use it. By the way, that table also can solve the following problem. For example, I ask you, okay, I toss 2 die, and once I have an outcome, say 2, 3, I can calculate the sum. 2 plus 3 will be 5. Here, for example, 4, 4, 6. The sum is, okay, the sum is 10. 6 and 6 is 12. And if I substitute each pair by the sum, I will know how many outcomes has the sum. Okay, 2, 3, 4. Okay, let's actually it's missed here, but I could do this a little bit later, maybe. So, for example, let me do the following. I substitute each number now for the sum. Okay, so 1, 1, I substitute by 2. And actually what I have to do, instead of writing the pair, I will just add this number and that number. So let me erase everything, and I will do this much faster if I want to find the number of sums. Okay, so 1 plus 2 is 3, 1 plus 3 is 4, 5, 6, and 7. Okay, next line, I have 2 plus 1, 3. You see 3 and 3 repeats, but in different way. 1 plus 2, and this is 2 plus 1. Okay, 2 plus 2, 4, 5, 6, 7, 8. Okay, next line gives you 4, 5, 6, 7, 8, 9. Then you have 5, 6, 7, 8, 9, 10. Okay, here we have 5, 6, 7, 8, 9, 10, 11. And that one is 7, 8, 9, 10, 11, 12. So for example, here is just a bridge between the combinatorics and probability theory. Question: if you toss 2 die, which sum will show up more frequently with bigger probability? Okay, so let's look. Number 2, so the sum 2 happens only in one case. Number 3 in 2 cases. Number 4 in 3 cases. Number 5 in 4 cases. 6 in 5 cases. Then 7 is in 6 cases. Okay, and then you see 8, again 5 cases. 9 in 4 cases. 10 is in 3, 11 is in 2, and 12 is only one like 2. So you can say that the most frequent sum happens if you get 7. And the probability is what? The number of ways to get the outcome divided by the number of possible outcomes. The number of possible outcomes, this is exactly what combinatorics is doing. 36. And if you want to ask yourself what is the probability to get 7, you count 1, 2, 3, 4, 5, 6 and divide by 36 and you get 1/6. So the probability 1/6 to get 7. And what is the probability to get 12? Only one possibility. It will be 1 over 36. Oh, sorry, let me just correct. So, yeah, one probability out of 36. Yes, it's very small probability. 6 times less than the probability to get 7. And for example, 4. What is the probability that the total sum will be 4? 1, 2, 3. Okay, 3 divided by 36 will be 1/12. Twice as less than 1/6. Okay, but this is a different problem and we'll not touch that problem. We concern only the combinatorics. Okay. Okay, next is the same problem, electing 2 club officers. You see, let's look at that problem. Okay, you have club N, and now we want to pick, besides the president, also a secretary. How many ways could you do this? Okay, choose a president and a secretary. How many ways to choose president and secretary are there? Now the answer will be different. Okay, let me just cross that one. Now let's solve in this exactly the same way as we solved the previous problem. So we have secretary S and president will be P. Okay. So secretary could be used Mike, Adam, T, or H. Now president could be used also M, A, T, H. So question is, what is the what is the number of possibilities? It's a little bit different story. We have here is a restriction. In 2 previous problems we solved. No restrictions here. Any digit from 2, 4, 6 could be the first digit, and any digit could be the second one. Likewise here, any outcome of 6 could be taken in the first dice, and the first die, and also 6 in the second one. Here we have restrictions. So first of all, if you choose M, Mike, as a president, you cannot choose Mike as a secretary, because it will be the same person. So we have to eliminate the square, M and N. Likewise, A and A, T and T, and H and H. So we eliminate the whole diagonal. And after that, now we consider the following: MA, MT, MH. Okay, AM, AT, and AH. Now TM, TA, and TH. And finally HM, and HA, and HT. So we consider all possible cases. So how many of them? Remember that MA and AM are different pairs, because here is M is the president and A is the secretary, and here, in this one, A is the president and M is the secretary. You see, do you feel difference? Okay. So, how to calculate the number of ways? You can count, of course, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, yeah, also 6, so 12 of them. But let's look. Imagine that these squares also filled. How many squares do we have total? We have 4 letters here, 4 letters here. So total number of squares will be 4 times 4. So the first part is the same as in the 2 previous problems. Multiply the width and the length. But after that, we have to subtract 4 diagonal squares because they are not filled. Minus 4. And so you have 16 minus 4, which is 12. 12 possibilities. So the answer is 12. Now, but next problem, you see, in this case, A and M are different, and MA, there's two different pairs. Now, next question is find the number of ways Club N can appoint a committee of 2 members. So now, next problem is committee of 2 members. Okay, so how many ways? Number of ways. Okay, will it be the same or not? If you choose a committee consists of 2 people, right? Committee of 2 members. So it's not important who is the president, who is secretary, just 2 people. It's like a set of 2 elements. And we discussed many times, if you have a set, it doesn't matter the order. The order is not important. So therefore, MA and AM will be the same, likewise MT and TM, and you have the symmetry with respect to this diagonal. And so therefore, if you have a committee with M and A, so therefore AM should be crossed, because we already have chosen committee. So the number of ways equals only 1/2 of the previous number of 12, equals 6. Okay, this is 12. And 6 are this one, 1, 2, 3, 4, 5, and 6. And those one will not be counted. You got it? So we have a restriction, and here, so in the second problem we consider sets, no order. In the previous one we consider order. And you see there are 2 different kinds of problems, with order and without the order. Okay, now next page is about tree diagram, and I actually explained in 2 different ways how to find it. So actually what's written here is exactly the same as I explained on that tree. So you have 3, you start with the first digit, 2, 4, 6, and then each one extend as it can be extended, and you get the numbers. But actually, you see, this problem is a little bit different, which considered here. Okay, this is a different problem. Next question. How many, okay, 3-digit integers with the digits 2, 4, 6 are there. Okay, so assuming, okay, now it's important thing. Okay, now let me try it. Now it's important thing, so restriction. Repeat it if there is no repetitions. Key. No repetitions. It's a little bit different problem. So see, for example, you can write 222 or 66 or 44. But now if you take 2, you cannot extend with 2. You can extend with 4 and 6. Okay, let's solve this problem independently. Okay, in the beginning, erase. Okay, in the beginning you have a root. Okay, root. Okay, and what is the first digit? 2, 4, or 6? That's right, 2, 4, or 6. Now, suppose we start with 2. What could be the next digit? 2 cannot be. So that branch must be erased. So we have 2, 4, or 6, right? Now, if you take 4, then how we can extend? We either extend with 2, okay, let's separate, or 6. And finally, if you start with 6, you can extend with 2, and then extend with 4. Now we have 2-digit numbers, 24, 26, 42, 46, 62, and 64. But we are considering 3-digit integers. So we have to extend one more. Okay, 4, how to extend? We have 2, 4, and last one is only 6. Only one possibility, 6. 2, 6, how can we extend? Only with 4. 4, 2, we extend only with 6. 4, 6, extend only with 2. 6, 2, we extend only with 4. And 6, 4, we extend only 2. And now you see all the 3-digit numbers. 246, 264, 426, 462, 624, and 642. How many of them? As many as the number of paths from the root to the end, or, which is the same, the number of leaves. 6 of them. So answer, okay, 6. 3-digit numbers. And all of them are written here. I could write as follows. I could write all of them. 246, 264, let's just write 426, 462, 624, and 642. Okay, by the way, what I wrote here from the tree gives a little bit different solution, and also gives me an order how to arrange all the 3-digit numbers and don't miss anything, and don't write the same number twice or 3 times. So how do you do this? You first consider digit 2. Okay, this is the same as to start with. Now after that, what can you write for the other two digits? Either 4, 6 or 6, 4. So the first group is arranged. Now if you start with 4, the other two possibilities will be 2, 6 or 6, 2. Another group. And here you have first digit 6, and then you have 2, 4 and 4, 2. So you have 3 groups. Each one consists of 2 possibilities. So the answer is actually 3 groups. 3 groups times 2 numbers in each. 2 numbers in each. Sorry, not enough room, but the answer is the same 6. So therefore, instead of counting the number of paths or the number of trees, you multiply 3 by 2. Again, you have the so-called product rule, which we'll consider once again a little bit later. Okay, so here is some example of some geometric example, and let me just also consider it using the systematic listing methods. So systematic listing method is just count all of those and write them down. So consider the following problem. It's also written, by the way, in the book, in your textbook. So here is the problem. Okay, you have triangle with the base AB, the vertex is D, then you take 2 points E and C and connect E with A, so C with A, E and B, and E and C. So you have some number of triangles, so say ADB or ECB and so on. How many triangles? How many triangles are there? So the answer here is 12. Okay, let us look. We mean distinct, different triangles. Okay, how do we do this? If you start drawing the figures, you will confuse yourselves immediately. So the only real approach here is just to write all triangles with letters. So first write all possible letters. What could be the letters? The first letter could be A. So how many letters do we have? We have 5 letters, right? And so we have to choose. So we have 5 letters. Let's write them as set A, B, C, D, E. Okay, and then we have to choose 3 of them. Okay, choose 3 of them. Okay, so let's write A, B, C. How do we do this? The same way as I just described for the numbers, 3-digit integers. So start with letter A. A, B, C, A. By the way, so here we do not need to write ACB. ACB and ABC is the same. It's the same triangle. So we consider that letter A is the predecessor of B, B is predecessor of C, C is predecessor of D, and D for E. So if you write, say, BDE, then DBE is the same. So we just write for small letter, previous letter and then next letter. So let's write A, okay, with B. What could it be? ABD, okay, ABE, ABC. So start with AB. And then we can add C, D, or E. We have that one, right? So all letters are here. Now let's start with letter B. The only what you can write letters, bigger ones. So we can write BA. So for example, if you write BAD, it's already here, ABD. As I told you, we have to write only the letters next after B. So we have BCD, BCE, so use BC and BC. So we have BCD. So we have all those. Okay, finally, let's start with C. We have only one possibility, CDE. So it looks like how many? 3, 5, 6. But now let's solve this as follows. We used here A and B, and then we added C, D, and E. Let's start with A and C as a pair. Okay, what can you add? You cannot add B because ACB will be the same as ABC. So we add D. Also AC, we add E. Okay, so we have those ones. That's it. So AC. And finally, here also, if we start with A, we can write AD, and then the only possibility to add, it will be ADE. Okay, next, we have BCD, BCE, but now let's write BD. BC we used, okay? BD, BDE, the only possibility, okay? And what else? If you use, and also we can use BE, but what's next? No matter what you write, suppose you write A, it will be BEA. It's already here, BEC. BEC is the same as BCE. And BED is the same here, so nothing. And finally here is, if you write C, the only possibility is CDE. So now we know, because we have a special arrangement, we know that all the triplets are taken. How many of them? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10. Oh, do you know what I forgot? I forgot letter F. So this one, you see? But maybe it's for good. Because 10 is, what is 10? because we used letters A, B, C, D, let us think a little bit more abstract. Let's write these letters A, B, C, D as just vertex located on the circle. Suppose here A, B, maybe this way. So A, B, C, D, E. Okay, without F yet. We add more. Now, and we have to take triangles. But now I'll tell you important thing. If you have a triangle, say ABC, what's left over? E and D. So if you draw a triangle, you also at the same time mentally could draw ED, a segment. So the number, if you want to count the number of triplets, like ABC, it is the same as to count the number of segments in the complement. You see, ABC corresponds to ED. So if I pick something different, say ADC, then it corresponds to the segment BE. So we can say that to pick three, choose three of them is the same, the number of those is the same as, okay, I erase that part. Okay, it's the same as the number of ways to choose only two of them. So we have to find how many segments you can take. Okay, each triangle corresponds to a segment with the ends of the letters complement to this set. So if you take BCA, BCD, then the complement will be DE, will be AE. So that triangle corresponds to segment AE. So to calculate the number of triangles is the same as to calculate the number of segments. So we have to draw all possible segments. If you draw all possible segments, you get you get a pentagon, 5 segments, and also you have to draw all the diagonals. So 5 plus 5 equals 10, and we got exactly 10 here. Okay, a little bit later in the last chapter, you will know that this number is very interesting. It's written, in the book it's written as follows: C 5 3, okay, which is the same as C 5 2. It's just my step, I jump to the next section. But also in mathematics, C means choose. Choose 5, choose 3 out of 5, choose 2 out of 5, and we know that they are the same. And also is denoted as 5, choose 3. So that one is symbol used in all mathematical books. 5, choose 3. So the number of ways to choose 3 objects out of 5 or 2 objects out of 5 is the same, and it's equal to 10. Okay, now let's continue solving the problem. Now we involve letter F. What you have to do? First of all, you have to add triangle to the group A, starting with AB. So it will be ABF. Now, next one is ACF. Okay, one more. Now here you have to add BCF. Here you add BDF. And CDE you can add CDF, and it looks like the same. That's it. But now because one more letter is here, we have to add one more triangle, namely it will be DEF. The last so okay, 5 letters. You see 5 letters. Now I have to choose for 6 letters, and F here is letter F. Okay, so new letter. So how many triangles did you add? 1, 2, 3, 4, 5, 6. So the answer should be 16. Okay, despite the fact that in the book it's written 12 different triangles. So did we make a mistake? Fortunately not. The only kind of mistake. We were asked about triangles. But what is a triangle? Triangle is a figure consisting of 3 segments like that. If you have, and 3 points are not on the same line, it means that, another word for that, they are not collinear. If you have 3 points on the same line, it's also a triplet, but not a triangle. So we have to eliminate such combinations. Let's look. For example, AFC must be removed. You see, AFC are on the same line. How about okay, let's look. AED. Oh, I didn't write it. So ADE must be removed. ADE or AD. Okay, next. Let's check every single one. ABC is ABC is good. ABD good. ABE good. ACD good. ACE good. ADE we already removed. BCD must be removed. It's not a triangle, it's just 3 points on the same line. Now BC is okay, BDE is okay, BCF, that triangle is okay, BDF, BDF actually they're not on the same line, but they do not form a triangle on this picture. So BDF must be removed as well, by a different reason. Because they do not form, there is no segment connecting B and F. Now CDE is okay. CDF also it's not a triangle, because the segments don't, and DEF also must be removed. Okay, so how many are left over? Let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, what is one more? Okay, let's check once again. 1, 2, 3, 4, 5, 6, okay, 7, 8, 9, 10, 10. Okay, so what didn't choose? Okay, when I used letter F, something happened. So say BCF. Oh, no, BCF is here. BCF. Oh, BCD is already BCF. Okay. Now BDE, BDF is here. CDE, CDF, and DEF. Okay. Do you know? So maybe. Okay, maybe let's count once again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So something AFB. So it's in here, ABF. Yeah, okay, so let me just don't check this. It's just when you, okay, that example, by the way, shows when you write all the possibilities, you can make a mistake. That's why special approach is used in combinatorics, which avoids the listing way and use a little bit different way. Okay, let me finish on that and we'll go to the next chapter.